Thank you, Alan, for your very kind introduction. And I'm really pleased to see many friends here. And I want to congratulate Darsh on his annual lecture series. Can you hear me in the back? No? It is on. Can you hear me now? Thank you. Alan pointed out my experience in academia and industry, so I thought I'll start with a true story that's attributed to Woodrow Wilson, who was president of Princeton University before he became the president of the US. And when he moved to Washington, soon after that, the story goes something like this. A reporter asked him, Mr. Wilson, why did you leave the comfortable surroundings of academia, especially an Ivy League university like Princeton, to come to, of all places, Washington, D.C., to which President Wilson responded, so I don't have to deal with politics anymore. So I thought, I cannot quite say that, but there is some truth to what he said. So I'm really delighted to have the opportunity to be here and to talk a little bit about something that we all worry about. And I knew for quite some time, and I learned more today, that IIT Chicago has had substantial activities in the international arena, especially in science and engineering, at a time when science and engineering is increasingly seen as the currency for economic prosperity and growth by many countries, large and small. I want to start at the beginning of NSF. I'll say a few things about NSF. Many of you know this, but for completeness. This is the picture of Dr. Vannevar Bush, and I'm very fortunate to still be the Vannevar Bush Professor of Engineering at MIT. I never had the privilege to meet him. He was the first dean of engineering at MIT. So I literally sat in the chair that he once sat in, but I never met him. He passed away in the 1970s. He was the head of what would be the equivalent to the head of NASA right now. He was science advisor to several presidents of the US before there was a formal science advisor. He built one of the earliest computers in the electrical engineering department at MIT. He was president of Carnegie Corporation, and he was also one of the two co-founders of what is now known as Raytheon. And so in the 1940s, at the invitation of the White House, he wrote a report, a copy of which is on your right-hand side, called The Science, the Endless Frontier. There was an interesting thesis in that report, which was exceptionally controversial at that time. And the thesis was simply the following. The economic prosperity of any country very strongly depends on innovation. I think that we will all agree. Innovation, technical innovation, necessarily comes from basic research in science and engineering. That was a controversial part. This was before there was an engineering science and so forth. And further, he argued that it is not only the role of the federal government, but it's the obligation of the federal government to nurture that innovation enterprise. And that's best done at universities and colleges, because that's where free opportunity for free thinking, free exploration takes place. And it's universities and colleges are also the places where young people are educated and nurtured, and they become future leaders in industry. And so this was his thesis. It was rejected the first time it went to the White House. President Harry Truman accepted it in 1950 and created the National Science Foundation based on that report. The first year annual budget of the National Science Foundation for the entire country was $212,000. This year's budget from the President to Congress for NSF for 2013, which starts in about 2 weeks, is $7.36 billion. So we've come a long way, but in the views of many scientists and engineers, and especially people from academia, we haven't come long enough or far enough to meet all the demands that we have on the science and engineering enterprise. So let me put, before I go to NSF, let me start with the US. Nobody would argue that at least in the last 50 years, especially after the Second World War, the US has been the undisputed innovation leader in science and engineering. I mean, many countries have produced extraordinary innovations, but collectively, if you take the sum total of all of this based on any metric, whether it's creation of new technologies that have changed the world, from Google to Yahoo to iPhone and so forth, to the number of Nobel Prizes in basic science, you take any metric in science and engineering, nobody would question in the second half of the 20th century, the US has been the undisputed leader. There are many, many factors to this, and none of this is a secret to you. I mean, it's unknown to any of us. We've been the innovation leader. The US is the magnet for talent from all over the world, and this university is a very good example of this. I don't know the numbers at IIT Chicago, but I know the numbers at MIT, at least as of 2 years ago. The School of Engineering, of which I was dean, there are 375 professors at MIT. Of 375 professors, 43% are foreign born, myself included, and many of you here in the room. And they not only were born and raised abroad, they got their first degree in engineering abroad. So let's think about that. Some other taxpayer paid 22 years of expenses, not only to grow a child, to a young person to age 22, but to educate them to age 22. And that magnet, the US being a magnet for talent, has huge economic implications for this country. And that has resulted in it's one of the many, many contributing factors to our leadership role in innovation. No matter which ranking you look at around the world, by anybody's metric, out of top 10 universities, at least 6, 7, or 8 of them are still American universities with all their problems, with cuts in state funding, et cetera, still. The challenge is to keep it that way. So some of the other factors are we have a wonderful system of public-private partnership at all levels, but also opportunities for people to go from no education in a family through community colleges to a state university system to an elite private university in various stages and steps. And that opportunity still exists, even though it's being strained quite a bit. So at a time when countries like China, India, and others are investing very, very heavily, much more than we are able to do, there is talk about are we losing the leadership? Yes, if research funding is absolutely essential for leadership, sustained leadership, and sustained funding is essential for sustained leadership. But is that sufficient? It's necessary, but is that sufficient? I would argue that money is absolutely necessary, but in addition to that, one of the things that made the US innovation system so powerful over at least the last 50 years is the fact that we not only had investments, sustained investments in basic research, education, we also created, nurtured, and refined institutions that fostered things like scientific peer review. The NSF is a very good example of this. As imperfect as NSF is with respect to its peer review system, other countries view us as the gold standard. So just in the last 10 years, the following countries created a government agency in their countries modeled after the US National Science Foundation. China, India, Ireland, Malaysia, Singapore, South Korea, etc., etc. And so it's not only the institutions that do things like scientific peer review, that also focus on research integrity, respect for intellectual property, and protection of intellectual property, and also mobility of people, and an open and transparent system. I think these are essential ingredients of this. The reason I want to mention this is because this is an area where the world looks up to agencies like the National Science Foundation or National Institutes of Health. And here we have a major global leadership role to play. And last but not least, we have unique models for university, industry, national lab interactions across the board. And again, IIT Chicago is a very good example of that kind of an interaction. So let me talk a little bit about NSF before we go to the global scene. Our charter from Congress is to sponsor fundamental research across all fields of science and engineering research and related STEM education, that we don't take care of handling education. That's the role of the Department of Education plus local school districts, et cetera, et cetera. But our goal is to do research into best educational practices that somebody else takes up later, with about $7 billion in annual support. We are unique in many respects as a federal agency. We are the only federal agency whose mission is not to push a particular mission. NASA's mission is air and space. DOE's mission is energy. NIH's mission is health, human health, et cetera, et cetera. NOAA's is atmosphere, oceans. Doesn't mean we don't have a mission. Our mission is not to go after any one particular thing. The only thing we don't do is what NIH does, that's human health. Everything else in science and engineering is fair game, focusing on basic science. The other distinction is that we are the only federal agency mandated with funding all fields of science and engineering. So there are many, many disciplines where if we don't fund, nobody else will fund. So that makes my job extremely difficult. So if there is a budget cut or zero budget increase, I don't have the luxury of the CEO of a $7 billion company who can say, I'm going to close a division, and 10 years from now when the economy picks up, I'll put it back in. We cannot do that. If we do that, university departments will close. Our leadership in an intellectual discipline will disappear. Once it disappears, it will never come back. So we don't have the luxury of fine-tuning the response to budget needs year-by-year basis. And unfortunately, we are the only developed country which doesn't have a multi-year budget process. In fact, we do retroactively through continuing resolutions. So this is a major problem. We are also unique in another respect. We do no internal research. All the money we receive goes back to the community minus the cost of doing business. So let's talk about cost of doing business. Our overhead rate is less than 6% on a $7 billion budget. Congress repeatedly asks us, why are you spending this? Why are you spending that? In every one of my testimonies, my response is we are already lean. If we get any leaner, we'll be extremely anorexic. And we cannot afford to trim fat because the staff have to handle 56,000 proposals a year with 1,400 staff members. Plus we run the only research station in the South Pole for the entire US government. And so this is a huge responsibility. NOAA's work in Antarctica is overseen by NSF. NASA's work in Antarctica is overseen by NSF. So we have a lot of responsibility to do this, but the overhead rate is less than 6%. Last year we supported nearly 300,000 individuals in the US in nearly 2,000 institutions. These are not only universities and colleges and community colleges, they also include some schools, high schools, K through 12 school systems, science museums, a NOVA television program, science activities in public radio, a variety of other activities. What is the impact? So NSF has been in existence for 62 years. I can talk about many different things. I'm going to talk about three things. First, let's start with students. NSF started the Graduate Research Fellowship Program in 1952. So this year is the 60th anniversary. First year we offered just a few dozen graduate fellowships. In 2010 we offered 1,000 graduate research fellowships per year. In the last 2 years we have doubled them. So now we offer 2,000 per year, even in this economic climate. And I made a conscious decision with the unanimous support of my senior leadership team that no matter what happens to the economy, there are some things we want to protect on grounds of principles. And those principles are supporting young scientists. So it's graduate students, postdocs, and young faculty members. So we double the number of graduate research fellowships. Every other year, we will increase the long overdue cost of living allowance plus tuition subsidy. We can't do it every year and keep the number at the double level in the current budget climate, so we're trying to balance that. So since 1952 until now, we have given 46,500 graduate research fellowships. Okay? So the person who received the graduate research fellowship in 1952 was 22 years old. So they're still 82 years old. Given the average life expectancy, the vast majority of the 46,500 NSF graduate research fellows are still alive. Okay? So that's the first point. In addition to that, every year we support 40,000 research assistants per year in the US through research grants that are given to universities and colleges. So let's see how these 46, I'm not going to talk about the research assistants, I want to talk about the 46,500 graduate research fellows. They have to be American citizens or permanent residents. So foreign nationals are not eligible for those. So since 1950, 197 Nobel Prize winners have been supported by the National Science Foundation. Okay? Let's put that in context. Since 1951, the total number of Nobel Prizes is 510. 40% of all the Nobel Prizes in the world, 40%, since 1951 have been supported by NSF. And NSF has supported 70% of all the US Nobel laureates. In some fields like economics, we've pretty much supported all of them. In other areas, we've supported many of them. So last year, 2011, we supported 7 Nobel Prize winners. So last year I had a chance to meet with the Swedish Academy of Sciences and the King of Sweden. Just a few weeks before the Nobel Prize ceremony, I made 2 points to them. One is we have the burden of selecting future Nobel Prize winners on the basis of potential rather than accomplishments many decades before the Nobel Prize Committee identifies them, point 1. Point 2, on average, we've given them more money than they have given. Okay. And both are true. So that, and then I mentioned graduate research fellowships. 38 out of the 46,500 NSF graduate research fellows have won the Nobel Prize. Secretary Steve Chu was an NSF graduate research fellow, and many, many others. So that's a very high hit rate. Let me take another metric. 440 out of 46,500, that's 1%, of all NSF-funded graduate research fellows have been elected to the US National Academy of Sciences. So I'm told by President Ralph Cicerone of NAS that that success rate is almost an order of magnitude higher than the success rate of an average American university in recruiting a faculty member who will be elected to NAS. So this is on the basis of potential, not on the basis of performance. So this is sort of the academic track record or the scientific track record. Let me now talk about the economic track record. And I'm going to come back to that later in the talk. So there are many ways in which we can look at it. In the 90s, so one of our mandates is to fund basic science at a time when the attention span is very short and at a time of significant financial constraint, when people want results very quickly. We are the only federal agency with a mandate to look long term, because scientific results, basic science, is not going to produce dividends next year, may not even produce in the next 5 years, but we have to have the patience. So let's look at some examples of what that patience has bought us over the last 62 years. In the 1960s, when the Department of Defense started to fund GPS primarily for defense and military and espionage purposes, NSF funded mathematics and computer science before there was a field of computer science, formal field of computer science, for many decades. That led to the creation of computer science departments around the country, and I'm going to show one data point shortly. And at that time, if NSF had asked the question, what is the return on investment next year for GPS, Apple would not be able to make iPhone 5 today. The technology that goes into it, who would have thought? Who knew in the 1960s that we will all be carrying GPS in our mobile devices and walking around? And this is so much investment from NSF has gone into the basic research. In the 1970s, when American industry thought that mathematical and process modeling was too academic, NSF invested very heavily into that. And that led to rapid prototyping, which played a huge role in the 80s and 90s in our economic and manufacturing competitiveness. In 1995, NSF awarded a fellowship to a young graduate student to do a purely academic exercise, PageRank method, Sergey Brin at Stanford University. And that was the nucleus of what turned out to be Google. NSF cannot take credit for Google. We will, but we cannot. But that basic research did play a role into this. Let me give a more recent example. In 1999, when the National Nanotechnology Initiative was launched at Caltech, NSF funded nanoscience and nanoengineering centers. So we have data points in the last 13 years. Those centers alone, which were funded purely to foster basic science, since 1999, have created 180 companies that involve 1,200 major corporations, involving tens of thousands of jobs. So that's the economic impact of this. So this brings me to another story about economic impact. This is the story of Dr. Michael Faraday in England, who first produced electricity in his lab. So the story goes something like this. This is narrated in Maggie Thatcher's autobiography. Mr. Faraday goes to see the politician, the Treasury Secretary or the Chancellor of the Exchequer in the UK, William Gladstone. And Mr. Gladstone asks him, why should the British taxpayer fund your curiosity? What is the value of electricity? To which Mr. Faraday responded, sir, one day you will tax it. So my point is that NSF receives $7.3 billion a year from a US taxpayer. The return to the US Treasury from that investment is many, many times the $7.3 billion. That's the return on investment. So before I go to the international scene, let me just put NSF funding in context. This is academic research across all universities and colleges by field for all federal government funding. In computer science, 82% of all the university research in the US, the most recent data, is funded by NSF. In mathematics, 65%. Physical sciences, almost 50%. Engineering, about 40%. And all fields of science and engineering, including social, behavioral, and economic sciences, about 21%. So this includes university research, but this includes every federal agency, NIH, DOE, NASA, NIST, NOAA, et cetera, et cetera. Now let's go from the US to the world. So this is the most recent year for which we have data. If you look at global research investments all over the world, in US dollars, adjusted for purchasing power parity, the world is divided almost equally into three regions. North America, which is primarily the US, 1/3 of all the global research R&D funding of $1.3 trillion US dollars, 1/3 is in the US. Little less than 1/3 is in the European Union, all countries combined. And a little, just about 1/3 is in Asia, and that's the part that's growing very, very rapidly. And last year, for the first time in the history of science funding, the top 10 countries in Asia invested the same in R&D as the US did. Of course, we don't know how much of it is R and how much of it is D. It varies quite a bit. Another way to look at it, on the x-axis, you have R&D as a fraction of GDP. On the y-axis, you have number of scientists and engineers per million population. So it's normalized by country size in terms of economy and population. The country furthest to the right is Israel, the bottom. The country furthest to the top right is Finland. Then you have Scandinavian countries. So it's a busy slide. That's to make it easy for you. All the blue circles are Americas. All the orange circles are Europe, and all the green circles are Asia. So you add up the areas of all the circles, you get the global funding picture. Okay. And the US is the big blue circle in the middle. So you can see Singapore has the same investment. This was a couple of years ago. In fact, they're surpassing us. Singapore also has a very high concentration of scientists and engineers. South Korea, Japan, Germany, Sweden, Finland, Israel, they are in the innovation spectrum over there. Look at the lower left, and these countries are moving, trying to move very rapidly. Indonesia, Saudi Arabia, Mexico, Malaysia. India is also in the lower left corner still. China is after that in the big green circle. Now let's look at students. So this is the fraction of college graduates who are majoring, who are graduating either with an engineering degree or a natural sciences degree. Asia, 20% of all the college graduates are engineers. Now let's put the numbers in perspective. If you take all the college freshmen in all the 50 states of the US last year, add to that all the college freshmen in all the 27 countries of the European Union, and add to that all the college freshmen in all of Japan, that number last year equaled the number of college freshmen in China. Okay? So that's the absolute number. This is the relative number. Engineering, about 14% in Asia. In Europe, both are about 12%. In the US, natural science is about 11%, engineering 4.5%. 4.5% of all the college graduates get a degree in engineering. That's why institutions like IIT Chicago are very special in this enterprise. This number is actually dropping. So you could ask the question, how did we remain an innovation leader for the last half century at least, when the number of engineers we produced is so small and it's been declining? And one of the answers is that you could pick and choose anybody in the world who would come here and stay here. So if we start to lose that, you lose that ability to compete on a global scale. But that's also under strain, because these countries that are also investing very, very heavily are also increasingly have the ability to attract people back. And I think that's going to be a huge issue for us as we go. There is one even more disturbing trend in this. Only 1.43% of all the college graduates in the US are women engineers. Okay. And this trend is very disturbing for a variety of reasons, especially at a time when 73% of all the valedictorians in American schools are girls. 20% more women graduate from college than men do today in the US. And yet there is a severe attrition at the college level and then beyond, even at the professional level. So what can we do collectively? So the national academies are trying to look, National Academy of Engineering is looking at this issue. And NSF has put in place a couple of issues which don't yet address the undergraduate issue, but we've started addressing at the graduate and postgraduate level, which I'll come to later. Now let me move from these trends to the intellectual drivers. So we have so many things exciting about science. What is so special about science and engineering at this point in time in the year 2012, and what is NSF's role in this? We can give many different answers, but of the so many exciting things that are happening at the intersections of many different fields, engineering and human health, etc., we can talk about two things that cut through every field of science and engineering. This is what we call the new era of observation. So what does it mean in the NSF context? We have the scope, resolution, reach, and scale, and the refinement of instrumentation that can not only look billions of light years away to the edges of the solar system, to discover new planets, to do basic research at such far distances, or drill 3 kilometers deep into the Antarctic ice in our NSF facility. We can do all of that. We can go to the other extreme of length scale, You can take a single DNA molecule and manipulate it with a desktop commercially available instrument to a force of a piconewton, to a displacement of a nanometer, and you can also do these kinds of studies at a time scale of a femtosecond. So you can go from all of this, and you can not only study the biology of a neuron in the human brain, you can couple that with the psychology of the human mind in ways in which we have not done. So that experimental tool, combined with computational hardware and software and all the advances that have been made in there, with advances in theory, for example, the Fermat's last theorem was solved by Andrew Weil at Princeton, who was continuously funded by the National Science Foundation to solve Fermat's last theorem. We didn't ask him, what is the commercial application of your work? If we had asked him that question, he would not have done what he was able to do. This year's Turing Prize winner in computer science, Dr. Pearl at UCLA, he's had 27 years of continuous funding from NSF, theoretical work, and in computer science. So these are the kinds of things. Theory has played a huge role in this. We don't want to discount that. Citizen science. An iPad today has the capability to handle a terabyte of data per day. The new facilities that we are opening now, the telescope facilities, can produce 10 terabytes of data per day. So that's the scale of what we have. So this era of observation is also creating a new era of data and information. So our challenge as a funding agency is, at a time when fiction can travel at the speed of light through the communication channels and become fact without peer review, and once it gets out there, it's hard to undo it. How do you separate fact from fiction? How do you take massive amounts of data and extract knowledge out of it? And how do you extract useful knowledge out of mountains of data? How do you archive it? How do you preserve it? And how do you make it permanent across devices that evolve very, very rapidly? And also, how do you protect personal freedom, privacy, individual rights, intellectual property, and how do you maintain cybersecurity? And what new science needs to be done now so that 10 years from now we will be there? Add to that the issues surrounding open access to publications and data. And so this is the challenge that we face. And all of this is global, because more than half the scientific publications now take place with authors from more than one country. So given that we can have our own policy, but if somebody from another country is unable or unwilling to follow that, these policies are not going to do much good. So how do we ensure that? So this is where the policy arm of what we do at NSF comes in. Then we have the issue I already mentioned about core programs. So at a budget crisis like this, how do we make sure that we protect our core, and how do we protect our principles? And I mentioned that already. One of the decisions we made in the last couple of years is we will support young people no matter what happens. That's our #1 priority, and we will not waver from that. So if the goal is to fund the best ideas and the best people, you want to balance individual scholarship, because individuals can make a huge difference. They can create a field. I mentioned people who solve Fermat's last theorem, to people who do computer science work, to everything else. But you also need major facilities. So astronomy cannot do its job if you don't have the facilities. We need major facilities. How do we balance this? It comes from the field, and all the decisions we make about facilities are not made by me or not made by any one individual at NSF. It mainly comes from community. So in the case of astronomy, the astronomy community through the National Academies, 200 leading scientists publish a decadal survey every year, and they prioritize what they want to see. So in a tight budget, we ask them, what do you want to see? And that's how the decisions are made. It's not a corporate decision. So even though we do that, we also have to work with other federal agencies to address national challenges. These could be priorities. They are administration priorities. They are priorities for many different agencies. So everything I've listed here is multi-agency priority, where we work with other agencies. One of our largest initiatives is sustainability. So SEAS is a $200 million effort in every directorate at NSF, in every office at NSF. which involves a lot of basic research and core programs. Cyber infrastructure framework. National Robotics Initiative is a $75 million initiative that President Obama announced at Carnegie Mellon last year. NSF is the largest contributor with $30 million of those. National Nanotechnology Initiative, we've been there right from the beginning. The intersection of biology with mathematical and physical sciences and engineering, biomaps. Advanced manufacturing, where we do basic research, where NIST, DOE Basic Science, and Department of Defense do applied work. Cybersecurity, Materials Genome Project was just launched this year, and NSF is a key player in that, to cut down the time to go from design of a new material to implementation of the material by more than a factor of 2, while bringing down the cost. Computational and data-enabled science and engineering, real-time networks, and major facilities. So we have seismology network that we fund called IRIS that involves 140 institutions in 80 countries. So if there is a pre-shock to an earthquake somewhere far away, all the leading US scientists will have access to data immediately through this network. We have put in probes, 5,300 probes as of 2 months ago, in the oceans across the world that continuously monitor salinity, acidity, temperature, sea levels, etc., that beam the data in real time to an NSF-funded facility in Woodsole. And this is accessible by any scientist in the US. So these real-time networks are becoming very, very important. We started 2 new ones last year. The National Ecological Observatory Network, which is the first continent-wide facility. The second is the Ocean Observing Initiative along the East Coast and West Coast, along the Atlantic and the Pacific Oceans. So despite this economic climate, we have a number of facilities that have just been commissioned or about to be commissioned. On your top left is a facility called ALMA in the country of Chile. 1/3 of that is funded by the National Science Foundation. 70% of all the astronomy observations in the world are made in the country of Chile because of geography, and we want to be there. And several thousand students have worked there, getting their research work done. The middle one is the CERN facility, which recently announced the search for the Higgs boson, and NSF funds that research in many institutions in the US, even though that's not our facility. The top right is an NSF-owned plane that goes through atmosphere gathering data. The bottom 2 are facilities that I'll be going to open next month. The left one is a new supercomputing facility, the first one in the state of Wyoming. It's the NCAR Wyoming Supercomputer Center with $50 million from NSF and almost an equal matching funds from the state of Wyoming. And that will open on the 15th of October. The one on the right is a ship called Sikuliak, which is being built in Wisconsin. And it'll be commissioned on the 13th of October in Marionette, Wisconsin. It'll leave Wisconsin, go to the East Coast, come to Washington. From Washington, it'll go through Panama Canal and go to Alaska. In 2014, it'll go to the Arctic. It'll be a research vessel where hundreds of students, faculty members will be doing their research in the Arctic. It has light ice-breaking capabilities as well. And it'll be commissioned in about 3 weeks. That's owned by NSF. This is a facility called LSST, which has just been approved. It'll be in Chile, and it's a joint NSF-DOE facility that's being commissioned. And this facility will open in about 5 years. DOE will provide instrumentation for this. This is a facility which has been in litigation for a long time because it happens to be in native Hawaiian land. And if the release comes out, then NSF will commission this. And this is a solar telescope. It's the first solar telescope to be built in decades. And this has huge implications for weather patterns, etc. So I want to take just a few more slides to talk about what are the kinds of things that we can do on a global scale that will make a big difference in addition to all the other things that I've talked about. Sometimes people think it always requires dollars, and I would argue dollars are necessary for the vast majority of things, but not always. Here is one example of this. NSF's mandate is to fund American scientists. We are not authorized to send money abroad. The USAID is authorized to send American taxpayer money to developing countries. That's their mission. Until last year, They were doing their business unbeknownst to each other. USAID would fund developing countries. We would fund American scientists. Oftentimes, those American scientists will not have any connections to scientists in developing countries with whom they want to work. So Dr. Rajiv Shah, who's the head of USAID, and I got together. We launched in July of last year a new initiative called PEER, Partnership for Enhanced Engagement in Research. So what does it do? We decide ahead of time through a common proposal process. We solicit proposals from developing countries and we solicit from the US, they solicit from developing countries. We coordinate them through a common peer review process, which USAID doesn't have. And then we put the people together who already know one another before we fund them on both sides. So American scientists have very good access to infrastructure abroad, and developing country scientists have access to very good infrastructure at American universities. It's a win-win situation. We launched it last year with 6 projects. It doesn't cost NSF an extra penny of money. This year, the demand was so high, we had 45 projects. And we are getting calls from overseas versions of USAID wanting to partner with NSF. This affects now several $100 million of coordinated research funding with no increase in budget for NSF. These are the countries in which now there are lots of funding, and next year there will be even more, especially through Africa. The other item I want to mention is the question of what kind of role can we play as a science funding agency or as a country as greater and greater investments evolve all over the world. So I mentioned earlier, it's not the investment in science and engineering research that's important. What is equally important is the values, the principles, the policies, the procedures, and the institutions that nurture peer review, research integrity, etc., intellectual property, etc. The question is, who decides that? Who creates the policy? Who agrees to the policy? Who polices it? Who ensures it? Nobody at the present time. So we decided last year, at the invitation of the White House, in close collaboration with the State Department, that we will host for the first time a global summit on scientific merit review. And because we don't have a big enough room at NSF, we decided to limit it to G20 plus OECD countries, which is 46 countries. We actually invited 48 countries to come. My counterparts of the leading science and engineering agency, 1 per country from 48 countries. We didn't know what to expect. We were expecting about half of, they were coming at their own expense. We were not paying for anybody to come. 47 of the 48 came at their own expense. So we had 2 purposes of this meeting. Leading up to the meeting, we will develop commonly accepted principles for scientific merit review, so that in the future, if you want to collaborate and co-fund, there is the implicit understanding, you want to co-fund with NSF, these are our principles for merit review. If you don't agree to this, we cannot co-fund with you. And potentially, universities can take this up. If you want to have a collaboration with a foreign country, if these are the principles developed by funding agencies from 47 countries, it makes negotiations a little bit potentially easier. So that was the first goal. The second is we created a virtual entity of my peers from many countries called Global Research Council. And this will meet once a year. Every time it meets, it has an agenda that it has to complete and finish, not start. And leading up to that, it has to hold regional meetings to which every country is invited. And within the US, we coordinated through the Committee on Science, which I co-chair with the head of NIH and the deputy director of the Office of Science and Technology Policy. So Science Magazine covered this, and they asked me for one line that they could quote. What would I say about global science? And I picked this line: good science anywhere is good for science everywhere, provided that you have an open and transparent process for merit review, research integrity, intellectual property, etc., etc. That's the provided, that clause. Next year's meeting will be co-hosted by Brazil and Germany in Berlin. There are 2 agenda items for that. At the meeting, we will release the research integrity document, principles, which will be endorsed by all the funding agencies. By the way, the people who were assembled in one room in May at NSF were in charge of funding 95% of science and engineering on the planet. sitting around one table. If that group cannot come together and agree on the principles, I think we're in deep trouble. And this was the objective of this. Next year's second objective is to develop a process so that a few years down the road, we have developed principles for open access to scientific publications and open access to data, and also how we are going to pay for it. So this is the group that has assembled at NSF to look at the Global Research Council. I'm just going to finish with 2 or 3 more slides on innovation. Our main mission is basic science. All of our funding pretty much leads to publications. Many of them lead to patent, but very few of those go beyond that. So how do we make sure that we get the biggest bang for the taxpayer buck without necessarily taking money away from basic research and putting it for translational purposes? So these are some of the projects that we started last year, but I wanted to show you this graph. This is the innovation ecosystem, at least from the NSF perspective. Most of what we fund, to the tune of $6 billion a year, is basic research. That's on the left-hand side, pure discovery. The valley of death is over there. Then you have foundations, investors, and industry. Between that, we have a lot of things. We have SBIR program. So Qualcomm started with funding for SBIR funding from NSF. Now they employ 21,000 people. Symantec started with SBIR funding from NSF. Now they employ 18,000 people. So those are examples of funding 20 years ago, 30 years ago that NSF did. Science and technology centers, engineering research centers, etc. Last year we started a program called the NSF Innovation Core. The idea is this: at the end of your NSF funding, suppose you had a small amount of money, something on the order of $50,000, and a short period of time, six months. Can you demonstrate from your scientific funding what kind of product, process, or tool or technology can come out, or software can come out? And after that, I mean, we can nudge that. Universities currently pay for it. So last year we funded 100 of them with one education node at Stanford. This year we'll fund 200 more with 3 education nodes at Stanford, Michigan, and Georgia Tech. We have calls for 2 more nodes. The goal is to create a virtual national ecosystem whereby those institutions that don't have the infrastructure for licensing, technology transfer, intellectual property rights, etc., can tap into this national system through NSF. We also went to private foundations and created a new model. So we asked 2 private foundations if they liked the idea. They said, great, go do it. Said, words are cheap, but that's not enough. So they actually wrote a check to NSF so that we could do something that we cannot do with federal dollars. So that's the national ecosystem that we would like to foster. Just last week, we received a commitment from 2 major American corporations to provide $5 million each to leverage hundreds of millions of dollars of taxpayer funding in the engineering education area. So there are tremendous opportunities for us to leverage on a global scale. One other point on leveraging is a new program called Science Across Virtual Institutes. So this is to take existing NSF funding and going global. So in the case of mathematics, for example, we fund 7 centers in the US in 7 different universities to the tune of several $1 million a year. We had a group of them come together. We asked them, who would you like to work with abroad? We went to the government of that country that they identified and asked the government, we spend $6 million a year. Would you put in at least $6 million a year? They said, we will put in $20 million. This is the multiplier effect that Irving Jacobs was talking about. We did the same thing in wireless communications with Finland and with the European Commission to support young scientists. So there is a lot of opportunities on a global scale. And the other program that started for interdisciplinary research is called INSPIRE program, which I'll show here. This is all the interdisciplinary funding in the first 40 projects that were funded through this INSPIRE program. This is about $30 million program that was just launched 2 months ago. And next year it'll have a higher budget. And the last thing I want to mention, I want to go back to a point I made earlier. so last year, 42% of all the PhDs in science and engineering in the country were women. And that number is growing very fast. And yet only 26% of the STEM workforce. So even if you allow for the time lag, there are many, many national studies that have been done. And there are many complicated factors, complex factors. But one of the key factors that all of these studies have identified is the difficulties or the challenges of balancing a career with a family. And this disproportionately affects women scientists and engineers. So what can NSF do? So we initiated 2 policies exactly in 3 days. It will be 1 year in the East Room of the White House with First Lady Michelle Obama. And here was the goal of this. We set a national goal. 10 years from now, in 2021, we want to have the PhD level women scientists and engineer workforce to be 41%, which is yesterday's PhD level degree graduation. So that's 50% higher in the workforce than where we are now. And it's not just up to NSF to do this. So we partner with the Association of American Universities, Association of Public and Land Grant Universities. So the presidents of those 2 associations and we released an MOU saying that we will work together with the universities to make this happen. NIH, NASA, and others are partnering with us. We'll be announcing some additional policies for career-life balance in a few months. This is the pyramid that we are working with. This is a huge challenge. So if you look at high school graduation in the country for 2010, that's non-minority women, non-minority men, minority women, minority men. If you go all the way to advanced degrees in science and engineering, you can see how the proportion changes. And we are trying to target that, where I have to say we have a very long way to go. And this is something that we are focusing on through a number of venues, through an NSTC committee that I co-chair, through the national academies in partnership with the various associations of universities, professional societies, etc. So let me just close with that, and I want to make one point, and that is people ask, what are the greatest challenges that NSF is addressing? Of course, we want to address, I mentioned grant challenges, global leadership, etc. But one of the things we also have to do is to support somebody who does basic research, an individual scholar, a young person sitting in isolation in an office whose idea 20 years from now may change the world. That's how Google got started. NSF funded that student who started the Google. So people talk about the Sputnik moment. It's very important to galvanize a generation. But we have to remember, we put man on the moon before we put wheels on the suitcase. Wheels on the suitcase are very useful too. Let's not forget that. We were carrying a heavy suitcase around. Now we can pull it along. That's an engineering innovation. Seemingly simple, right? So there are many opportunities. So let me stop at that point. Thank you.